All the operations that we've talked about so far have been what are called binary operations. They apply to only two sets at a time. Union, intersection, difference, all binary operations. Well, there's a way that we can extend these definitions to operate on multiple sets in a very natural kind of way. So the way these start is we start with what's called an indexed collection of sets. That's these sets here, A sub 1, A sub 2, A sub 3, and so on. We also specify a universal set in case we need it. If we want to talk about complements or anything, we're going to have a universal set. And a non-negative integer n. That non-negative integer is actually optional. It's possible that there will be a finite number of these sets. It'll be A sub 1, A sub 2, A sub 3, up to A sub n, and it'll stop. It's also possible that we could have infinitely many sets in the list, in which case we're not going to need that n. So how can we define these things? Well, the definitions, I'm going to warn you before I go to the next slide, they're a little wordy, right? But they're all really very much saying what we already understand union and intersection to be. Right, so I've got four definitions here for the union and intersection of a collection of sets. And the reason we need so many is that the difference between the case where we have finitely many and the case where we have infinitely many is different enough that we really need another set of definitions just to make it clear. So what we're saying here is, first let's talk about the notation. Looking at the top one, this is saying the union as I, that's that index variable that we're going to use to index the sets, goes from 1 up to n, whatever that n is. Right? And so how do we define the union? Well, the union is the set of all elements taken out of that universal set such that the element is in some a sub I, right? It's the x is an element of one of those sets for at least one value of I. And then down here, you can see now maybe why we need a separate definition. There is no end here for us to talk about if we're talking about an indexed collection of infinitely many sets. In this case, we just say for at least one non-negative integer I, right? It has to be in at least one of those sets that are making up the union. And the intersection goes in a very similar, very predictable way. The intersection is the set of all elements of that universal set such that x is in a sub I for all I in our range, or just for all non-negative integers in the infinite case. So this is saying the same thing, right? It's saying the same thing as we saw when we were talking about union and intersection earlier. To be in the union, it has to be in at least one of the sets, and to be in the intersection, it has to be in all of the sets. So let's look at some examples, right? First we're talking about a finite collection of sets here, right? I is going to go from 1 up to 10. It's going to do the same thing on the intersection one. And you notice how I've defined my a sub I over here. A sub I is equal to the numbers from I to I plus 1, including the left endpoint, not including the right. Right? And my universal set here is the set of real numbers. So those are the values that we're talking about going into these a sub I. All right, so I want to know what the union and intersection are, but before we do that, just the way I generally approach something like this is try seeing what just some of these sets are. Right? Let's pick some numbers here. A sub 1 is the numbers from 1 up to 1 plus 1. That's 2. Okay, so it's kind of a unit interval, right? An interval whose length is 1 with one endpoint but not the other. All right, so let's see what happens if we keep going here a little bit. A sub 2 is 2 comma 3. Okay, good. Now I'm starting to see a pattern, right? A sub 3 is 3 comma 4, and so on here up to a sub 10, which will be 10 comma 11. So I'm talking about the union. what I'm doing is I'm saying take all of these sets and combine them together. All right, so if you kind of try to visualize this, let's think about a number line here. All right, a sub 1 is 1 out to 2. A sub 2, well, a sub 2 adds 2 into the mix, right? Because 2 is included in that one up to 3. Then a sub 3 is going to be 3 up to 4. And we're going to keep doing this, excluding the right endpoint, but then bringing it back in with the second set. So this is going to continue up to 10, 11. That's a sub 10. And we're actually not going to be able to bring that 11 in on that last one. So how would I describe the union? The union from 1 to 10 of the a sub I. This starts at 1, and then ultimately it ends up including every number up to 11. So that's how I would describe the union of those sets. It's all real numbers between 1 and 11, including 1, but not including 11. Now, how about the intersection? What is the intersection of these going to look like? Well, again, with the intersection, I'm looking for overlap. What do they have in common? And they're clearly not overlapping anywhere, except maybe I got to think about the endpoints. And they don't really overlap there either. 2 is in this set, but not that one. 3 is in this set, but not that one. So there are no numbers that are in all of these sets. So the intersection is going to be the empty set. So I have another definition here, and to illustrate this, I'm going to use that same collection of sets that we used on the previous slide, right? Exact same ones. So our definition here defines what it means for a collection of sets to be mutually exclusive or pairwise disjoint. Right? This happens if and only if no two distinct sets have something in common. Right? So in other words, you kind of pick them out in pairs. Pick any two of those sets. If they have something in common, then the collection is not mutually disjoint. I've got kind of a formal definition of that down here. Right? For every I and j up to our maximum, our n, if there is one, we can do this with infinite collections as well. Then if I take any two sets from the list, and that's what this part here is saying, and that's the part saying they have to be different, then their intersection has to be empty. They can have nothing in common. And this is actually what we saw with these sets here. And I think the picture I drew really kind of illustrated it. If you pick any two sets, they look like this, and so on. Pick any two. If there's two non-adjacent pairs, obviously they have nothing. Those two have nothing in common. And even an adjacent pair here at this endpoint, they have nothing in common. Right? So because that's true of every pair you can pick out of there, I would say a sub I, let's put the a sub I, are mutually exclusive or pairwise disjoint. Same thing. So we can take this idea of pairwise disjointness a little bit further. Let's say we have a collection of sets, just like we had before here. And again, I've let it go out to infinity. It's possible it could be a finite collection. And we have these two properties here. Right? First, they're mutually disjoint. Right? There's no if you look at it visually, there's no overlap between any pair of sets from the list. And this is kind of the new part, the union of these sets is equal to the bigger set, right? This is the set that we're saying they are a partition of. So If I wanted to just kind of illustrate this visually, right, let's say I have this set here, and this is the set A, and my A sub I, there's A sub 1, A sub 2, A sub 3, A sub 4, and A sub 5. Okay, so these individual sets, assuming I handle the borders correctly, yes, it looks a little bit like they overlap at the border, but assuming that there is no overlap at the border, right, assuming that these A sub I are mutually disjoint, then their union, if you take them all together, combined, they make up this parent set, right? So I would say that these 5 sets are a partition of this greater set A. So I've got another example here, and I've done a very similar definition, right? The definition here looks the same. What I've changed is first this I part, right? I'm letting this go off to infinity now instead of having a boundary, and I changed my domain, right? Instead of being just R, now it's R plus. So I'm looking only at the positive real numbers. And I'm going to claim that these A sub I are a partition of this set of the positive real numbers, right? And to see why, hopefully it's pretty clear to you that they don't overlap, right? These are really the same sets I was looking at on the previous examples. I've just let them keep going out to infinity, right? There is no overlap. And do they make up all of R plus? Well, yeah. And to see this, right, we can just kind of write this out. Let X be an element of R plus. Okay. If X is equal to an integer I, then X is an element of A sub I. If X is not an integer, then round down to the nearest integer I, and X must be between I and I plus 1. It can't be equal to them. If it were equal to them, it would be an integer, right? So it has to be strictly between those two. Therefore, X is an element of A sub I, right? So I've shown that every real number fits into one of these sets, right? So this collection of infinitely many unit intervals is a partition of the positive real numbers. So that wraps up our quick review of basic set concepts, set definitions. In the next section, we're going to start looking at proofs involving sets and kind of the specific techniques that are used to do those kinds of proofs.